Welcome to Unit 8, Section 5, Lesson 1, Video 2, Tessellations, Regular Polygons. In this video, we're going to look specifically at whether or not regular polygons tessellate. So the question is, which regular polygons tessellate? And before we can answer that, let's quickly review what a regular polygon is. A regular polygon is a polygon where all sides are the same length and all interior angles are equal. For example, an equilateral triangle is a regular polygon because all three sides are the same length and all three angles are 60 degrees. If we try to tessellate the triangle, we can see that it does in fact tessellate. If we look at the middle of the diagram, where all 6 vertices meet, and vertices is just the plural of the word vertex, which is the corner of a triangle or any shape, each of these angles is 60 degrees. If we add them up, we can see they add to 360 degrees. And we'll come back to that idea in just a second. Next, let's look at a square. Does a square tessellate? A square is a regular polygon as well because all 4 sides are the same length and all the angles are 90 degrees. A square does tessellate. And once again, if we look at the middle where the 4 shapes intersect, we know that the angles in a square are all 90 degrees. So where these 4 vertices meet adds up to 360 degrees. Next, we'll look at a hexagon. A hexagon is a 6-sided figure, and the interior angles of a hexagon are 120 degrees. A hexagon will tessellate if we look at a vertex where 3 of the hexagons meet, and we just said that each angle is 120 degrees, we see once again that the 3 angles where the vertices meet add up to 360 degrees. Based on these 3 examples, we can conclude that when a shape tessellates, the sum of the angles where the vertices meet is 360 degrees. Let's look at 2 more polygons. So do these regular polygons tessellate? First, we'll look at a pentagon. We can draw another pentagon here and one here, but in this example we can see that we have a small gap. Now the interior angles of a pentagon are 108 degrees. If we look where the vertices meet, we have 108, 108, and 108. We can see that they add up to 324 degrees, not 360. So what is the value of the missing angle? 360 subtract 324 is only 36 degrees. So there wouldn't be enough space for another pentagon to fit into this diagram. So because the angles do not add up to 360 degrees, the pentagon cannot tessellate. Next, we'll look at a heptagon, which is a 7-sided figure. And if we draw several more heptagons connected to it, we get this. And now we can see that if we try to draw a 5th heptagon to fill in the gaps, there's no way it will fit inside so that all the gaps are covered. And the only way we could do it is if we had an overlap. So the heptagon does not tessellate either. For a heptagon, the interior angles are 128.6 degrees, approximately. If we look at where the vertices meet, we can see that 128.6 plus 128.6 equals 257.2 degrees. So what is the missing angle? 360 subtract 257.2 would only be 102.8 degrees. So it is not big enough to fit another heptagon in that gap. Therefore, the heptagon will not tessellate because the three angles do not add up to 360 degrees. In fact, in order for a regular polygon to tessellate, its interior angle must divide evenly into 360 degrees. So neither 108 nor 128.6 divide into 360 evenly, so they will not work. However, in the previous slide, we saw that an equilateral triangle, which is 60 degrees, a square, which is 90, and a hexagon, which is 120, they all work because each of those angles will divide into 360 degrees. The only regular polygons that tessellate are triangles, squares, and hexagons. Please proceed to video 3.